off with is interval and set notation. Interval and set notation is different ways to write sets of numbers. Because realistically, if we talk about any set of number, there's easier ways to write it and there's harder ways to write it, depending on what the number is. Now, a set is a collection of objects. Braces are used, and I just realized I don't have notes sheets for you. I'll have those tomorrow. I completely blanked on that. So you will have those tomorrow. Braces are used to list a set of numbers. So when we talk about a set of numbers, we're talking about a finite group. So that could be something like, so we have this 1, 2, 3, 4, 5. And we'll list them all out. Now, can anybody see why this would be inefficient at a certain point? Well, we could do 1-5, but I've got to list them out, right? So if I told you, okay, using this, list the numbers from 1 to 100. That'd be a lot, wouldn't it? So using braces to list a set of members is nice in a small set. So if we only have a few, like this here where there are only 5, it's not bad. But once we start getting a certain amount, it gets harder to do it this way. Does that make sense? So we come about different ways using this same notation. And we call that set builder. Set builder is used to define the set in terms of the properties of its members. So here, as I just showed you with that, now with set builder, we can expand it a little bit further. That means in terms of the properties of its members. So if they are natural numbers, we can use it. We can say we're talking about the natural numbers greater than 0, which is easier than the one I did before because I had to list out each one. But with the natural numbers greater than 0, I've just listed every number. Essentially, I've listed an infinite amount of numbers without writing too much. And we'll get into it, x such that, or x is an element of the natural numbers. Yeah, I've got something here. Yeah. So the set of whole numbers. X such that x is greater than 0. And stuff like this here. Now, we're going to get more into this here in a second. But there's different ways to write these and define them. Now, on a whole, we won't use this too much beyond this here. Beyond this chapter, we won't use a lot of set builder notation because we don't define things that way. There are subsets in math, that deal just with sets. You can actually go and get your doctorate on set notation and how you write it. There's a whole thing on number theory. And number theory defines how we write variables in certain order. If you remember back to Algebra 1 when we talked about doing stuff like this. And adding and subtracting these and then writing them out. Have you ever wondered why we always go in alphabetical order? Whenever we list variables, A, B, C, D, X always comes before, how we do X before Y or A before B. You know what I'm talking about? Yes? And that's all defined in our kind of set theory. There's a whole math for it. But we're not going to delve into that because that gets way over the top way fast because people with doctorates deal with that. Now, each set has a subset. Does anybody have a guess what a subset is? Inside of one set, it's part of the whole. Is a set that is a part of a larger set. Is when all the members of set A are also members of set B. So if you're having a little trouble thinking about this, think about it this way. This classroom is a subset of the high school. Because everything in this classroom is contained in the high school, yes? That is a subset. The main definition of a subset is everything in the subset is contained in the whole. So it's when all members of set A are also members of set B. So 1, 3, 15, 27, 20. 1, 3, 15, 27, and 20. So everything in A is also in B, yes? So set A is a subset of B. Is B a subset of A? Why not? Right, everything in B is not contained in A. Yes? And that's what a subset is. That's all a subset is. Okay? So let's take this a step further. The x-axis, yes? The line contains every number from negative infinity to positive infinity, yes? And we dealt with, so if I make a straight line, so a number line, yes? We've dealt with number lines dealing with inequalities in Algebra 1, yes? What we can say, this is actually a subset of the xy, yes? Is everything on the number line contained in this plane here? And how about we take it, because this is what we call 2D, yes? What could we do from 2D? We would take it to, and is everything in the xy coordinate plane contained in the xyz? Yeah, everything in the xy, our 2D coordinate plane, is contained in the 3D, yes? Now, mathematically, we would call the number line, the first one we started with, R1. Yes? And this here is what we call a subset. It's a subset of R2, what we call the 2xy coordinate plane, yes? So we good with this so far? Well, and as we just saw, it's also of R3, our third XYZ, kind of what we live in, yes? What does that mean also, kind of following this logic? But this is also a subset of what? Whatever the fourth dimension is, yes? Well, that also means that it's also a subset of fifth, going all the way to our n, where n is any number. How many minds just kind of blew up just a little bit? Yes? But this is a little bit of logical mathematical reasoning. Because we could say this is true, we can go on and take it to the nth reason. Can we mathematically or physically show what a fifth, let alone an nth, the hundredth? No. But mathematically, it's sound. And this is kind of some of the stuff we can do in subsets. This is taking it to a graduate level, so be above what a 4-year degree would take. But this is some of the stuff we can look at with sets and subsets. Does this make sense? It's really at the core what sets and subsets are is just groups. It's a group of items, a group of things. Okay? And set builder notation is a way to write them. Is a way to write them. Okay? Writing subsets in set builder notation. So we said a subset is what? Contains some of the elements of the whole, yes? So looking at this here, 2, 4, 6, can anybody give me a subset? Just take a stab, anybody. 2, 4, yes. I can give you an even easier one. Ready? 2. So what does that also mean? 6, and we also have 4. So we can have just 2, we can have just 4, we can have just 6. So we can also have 2, 4, we can also means we can have 4, 6. Have we covered them all? There's 2 more. One of them would be what? 2, 4. There's nothing that says that it can't contain everything in the set. Okay? The other one, yes, is the set containing the empty set. So a lot of the times, if you've wondered up to this point, why do math teachers, especially some of them really don't like you putting a line through 0? It's because it's actually something different. This is when you do a line across it, essentially saying it's the empty set, there's nothing there, which is different than 0. Because we're talking about sets, things, items, yes? So technically 0 can be listed as a number. Here, we're saying that there's not even 0. 0 is not even listed. There's nothing there. Because if we talked about number of skirts that you own, when we list it, it would be 0. I don't own a single skirt. As surprising as that might be, I don't own any skirts. So for the set, when we list those numbers out, mine would be 0. So there is something there, yes? That's why we also have the empty set. So there's a slight difference between them. Now, for most of what you'll cover, especially in high school and most of your college career, having this as an empty set or talking about the empty set won't come up too much unless you decide to go into mathematics. But you saw here, 3 gave us 3, 4, 5, 6, 7, 8. That's not too bad, right? Let's look at the next one. Let's look at 4. So I'm just going to add one element. That is what these are called. So let's see how many we can get. What do y'all think? So we would have what? Well, we did list each one individually. Then what would we do next? EF. And then, so FG, why don't we do FE? FH. Four, 5, 6, 7, 8, 9, 10. Did we just pass up what the first one was? So we did 2. Now we're going to do what? EFG. EFH. EGH. And then we'll have FGH. There we go. And then EFGH. And lastly, we have the empty set. So we added 1 and it almost doubled, didn't it? Imagine if we added another one. The number of possibilities start changing and growing, yes? They would grow even more if we said that they weren't kind of transmittable, that E, I'm going to write this over here. So pretty much saying that EF and FE, if we said that these weren't the same thing, then we'd have to list the order. If order matters, then they increase. But here we're saying order doesn't matter, that those would be the same no matter how we wrote them. It limits it a little bit. Any questions on this here? Sets can be a little bit crazy. Yes? Okay. How many have heard of the different number types? You probably heard it at some point because we talk about the real number system, yes? And that's a group of numbers. Now, the first one we have is something called natural numbers. Natural numbers are naturally the numbers that you count on your hands and your feet. So 1, 2, 3, 4, 5, 6, 7, 8 going up. Now, realize natural numbers don't include 0. Natural numbers are 1 and up without decimals, no fractions. They are what we call the natural numbers. So 1, 2, 3 going on. So we're good with natural numbers, yes? As I just said, it doesn't include 0, correct? That is whole numbers. So when we call something a whole number, we're talking about essentially natural numbers, but we include the number 0. So it's 0 going up. And as you notice, the natural numbers are a subset of the whole numbers. Yes? It works out the whole numbers are a subset of the integers. Integers, where we add negatives. So now we have all the positive whole numbers, all the negative numbers, and 0. 1, 2, negative 1, negative 2. And the integers are a subset of whole numbers, and whole numbers are a set of natural numbers. So it means integers are whole numbers are natural numbers. Yes? Is a integer also a natural number? Not always, right? Because is 2 a integer? Well, 2 is an integer. It's also a whole number, and it's also a natural number. Negative 2 is not a whole number or a natural number, but it's still an integer, yes? So as we go up, some are included, some are not, and the ones above it. So we go with natural, whole, and integer so far. Yes? We also have something called rational numbers. Rational numbers are going to be any numbers that can be written as a fraction. Rational, ratio, rational can be written as a fraction. So if a number can be written as a fraction, it's going to be rational numbers. So I didn't include all of them, but we still have everything that's an integer is a rational number. But our fractions and these kind of decimals that will show up are not going to be any of these here. Questions on this here? So we good so far? Yes? Well, after rational, we have something called irrational numbers. And the main defining factor of an irrational number is that it cannot be written as a fraction. It is a non-repeating, non-terminating decimal. If it is a non-repeating and non-terminating decimal, it's considered irrational. And what encompasses all of this here is real numbers. And I can see it on your face, Eric. If we define something as real, it means something else must be. Yep. And we will cover what you call fake numbers. They're called complex numbers. But we talk about non-real numbers. How many of you think complex or non-real numbers are never going to show up? Nope. Anything electronic in nature, anything electrical in nature, deals with complex numbers. That TV in the back of the room, does it have the ability for electricity to flow through it? Is there any electricity running through it? So how can I define something that has the capability of doing or having electricity flowing through it, even though it's not there? That's where complex numbers comes in, because it hits a range where this is the property, but it's not there. So it sits in the complex range until the moment that it's turned on. And the same thing is true with capacitors. If you've dealt with or looked at computers and tubes and stuff that's turned on and off with electronics, deal with these complex numbers. And we can define them in equations by complex numbers. Now, if you're wondering and probably thinking that rewriting these natural numbers, whole numbers, integers, rational, irrational, real numbers is a little bit of a challenge, that's fine. They have shortcuts for it. Real numbers is we use an R with 2 bars. That is real numbers. So in mathematics, when that R with 2 bars shows up, it is understood to be the real numbers is what we're talking about. Natural numbers is an N with 2 lines. So when that symbol shows up, it's talking about the natural numbers. Whole numbers doesn't really have one. I've seen some do a W with 2 bars. Natural, whole. Integers. Anybody have a guess what integers is going to be? Almost. It's a Z. No. It's irrational. Anybody have a guess at rational? Q with a line through it. Everything makes sense up until integers and rational. And I'll go on and give you complex as a C. And these here are just ways to define what they are. So you're not having to rewrite natural numbers over and over and over again. Because a lot of the times mathematicians, if there's a shorter way to write it, they're going to do it that way. They're going to find the easiest and shortest way to do whatever they need to do. Are we good with this here? Yes, for the most part? So, writing the subset and using this kind of notation we just found of the whole numbers 50 through 54. Now, I'm going to show you there's different ways we can do this, because 50 through 54 is not a whole lot of numbers, especially whole numbers, because we're not talking about decimals or fractions or the irrational numbers. We're only talking about 50 through 54. So our first number is 50, and then we have 51. Then it would be that's it, because that is the set of whole numbers, because those are all whole numbers, yes? 50 through 54. Now, another way we can write it is our bracket X is an element. That little e looking thing is element. So what that's telling you or telling us is that X is an element of what type of numbers? So we'll use our fancy W, whole numbers. Such that what? What are we talking about the numbers? They are 50 through 54. So 50 is less than or equal to x is less than or equal to 54. So yeah, so this here, it's easier to write the top way, yes? Because there's only 5 of them. So say we were talking about not whole numbers, but real numbers. So we're talking about the ones that we have listed here, as well as 50.1, 50.11, 50.111, 50.11111. And we talk about anything between it, yes? Would I be able to list those out? But I can take this way here, and really, if we're talking about real numbers, we don't need anything. But we can write it and say that it's an element, well, put the eraser down. It's an element of the real numbers such that 50 is less than or equal to x is less than or equal to 54. So now we've listed any and all numbers between those. Can you all see these here? And once we get done with this chapter, this stuff is not going to come back up again. Okay? So here, the real numbers between 0 and 4. So, am I able to list out all the real numbers between 0 and 4? Well, no, there's too many of them. Yes? So what we're going to do is we can start off with our bracket, because most all these are going to start with the bracket. And then we're going to say x is an element of what? The real numbers such that what? 0? Yes. And that's it here. Questions on this here? Now, as I said, with this here, real numbers is really understood in most mathematics. So we could say a set of x, all real numbers x, such that 0 is less than or equal to x is less than or equal to 4. So if it was whole numbers, we would really pronounce this like we did on the last one. The set of all whole numbers, x is the set of all whole numbers such that, and we have our definition. Questions on this here? The integers, negative 1,000 through, or negative 100 through 100. So what are we going to start off with? Bracket, x is an element of what? Integer. So we would have our z such that now here's a question. Do we use the equal to or not? So through. So would we say we would include it or not? Okay. And that's it with this one here. Questions on this here? Any question on anything we've done so far? Okay. Okay. Now the next thing we're going to delve into, and get into is bounded and unbounded. So we're talking about interval notation is what we'll be doing next. But I'm going to do one more set. Numbers. This is the last one we'll do today, and we'll pick this up tomorrow, okay? So the set of real numbers, of all real numbers except for 4. So we have x, which is what? Well, the smallest number we can have is negative infinity, yes? Yeah. Is less than, well, we don't say equal because we can never equal negative infinity. Is less than x. Is less than 4, yes? So this right here is telling me all the numbers that are smaller than 4, yes? And we'd also have what? 4 is less than how many of y'all think there's probably an easier way to write this? Yes? So we can exclude the here. So we can say all real numbers x such that negative infinity is less than x is less than 4, and 4 is less than x is less than infinity. Yep. But when we say x is a part of the real numbers, what are we saying? It's a part of everything on a number line, right? So what are we saying it can't be? Such that what? X is does it what all of these are saying is the set of all real numbers x such that x is not equal to 4. It's everything else, isn't it? These three here say the exact same thing. Any questions on any of this here? We good with this here? Okay. That is where we will stop for today.